we live yet? Looks like we're going live. Okay, we're trying to go live. Okay. So, forming covalent bonds. How covalent compounds form their bonds and things like that. That's the topic for a graduate level research program. But this right here is a very, very simple explanation. Okay. You have two atoms coming together. The protons or the nucleus of one atom are attracted to the electrons of the other, and the protons of this atom are attracted to the electrons of this guy. So there's a mutual attraction between the nucleus of one and the electrons of its partner. So if you start at infinite distance, they don't feel any attraction or anything like that. As you bring them closer together, the protons and electrons start interacting. You get more and more attraction, more stability, and eventually you get a bond. If they get too close, though, the electrons start repelling each other. The nuclei, the nucleus of A and the nucleus of B, start repelling one another, and that repulsion goes up very, very fast. And thus, if they get too close, it's very unhappy very quickly. So this right here is the happiest place. So that is the bond length and the bond energy. This right here overall is not how it happens. That is not the actual explanation. It is far more complex than this. But this is a simple enough sort of thing that they can ask you about this on the test. And it's not entirely false. It's just that there's a lot more to it. Okay, so this right here is the better explanation. When two atoms come together, well, not just the two atoms, but when all the atoms of a molecule come together, they mix their atomic orbitals together in order to make molecular orbitals. And if their atomic orbitals are close enough in energy, they can do that, and they make these new molecular orbitals. And the shapes and the positions and how and whether they can mix is all dependent on if they have the same symmetry. There's a lot of higher level math in there. And then you take all the valence electrons of the atoms and you put them into those molecular orbitals in the various configurations. And that tells you whether you have bonds and what kind of bonds you have, and whether you have non-bonding electrons or lone pairs. And it's all very complicated, and we're not going to touch it. This right here, this first slide, this is the level that I expect them to ask you about. Possibly. This is something they could ask you about on a test. It's a very short, sort of simple thing. The nuclei of A are attracted to the electrons of B, and vice versa, and that's what lets you form a bond. We are going to build up to something more complicated than this, in that we are going to talk not about molecular orbitals, but about hybrid orbitals and valence shell electron pair repulsion and orbital overlap. And there's various ways we can build up to approaching molecular orbital theory without actually going anywhere near molecular orbital theory. So we're going to build up from here. We're going to do something more complicated than this, more in-depth, more correct, something that will allow you to understand why molecules make the shapes they do and why they form the bonds they do, without going into the nasty awfulness of this. Okay. So that was way too short for a single lecture. So I'm going to go ahead and just dive right on into the next one, presenting covalent compounds. So how do we write them down, basically? Chemical formulas. There's nothing particularly new here. We write down the element. We write down how many atoms there are of that element. If there's only one, we don't write the one. It's just assumed. So here we have glucose, C6H12O6. So remember, this is different from ionic compounds in that this is not a ratio. This is the actual number of atoms present, actually involved in this molecule. A single molecule of glucose does have 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. Okay. Now, the problem with the chemical formula is that it doesn't show structure. It doesn't show us how the atoms are put together, and that is important. Okay. Here we have one method of showing structure, and what it's showing us is isomers. Okay. Isomers are things that have the same chemical formula, but different chemical structures. So these are the 9 isomers of heptane. Heptane is this guy right here, 7 carbon atoms and 16 hydrogen atoms. Basic heptane is just a single long chain. Okay, the 7 carbon atoms long, and then each carbon atom has its valence filled in with hydrogen atoms. But as you can see, you can get, you pop the carbon off the end here and put it over there, and you have 2-methylhexane. Put it on this carbon instead, and it has 3-methylhexane. So, and then you can pop 2 carbons off, and you get 2,3-dimethylpentane, 2,4-dimethylpentane, or 2,2-dimethylpentane, or 3,3-dimethylpentane. Or you can pop the 2 carbons off, and instead of putting them on the main chain, you can attach them as their own little side chain, 3-ethylpentane, right? Or you can pop a 3rd carbon off. You get 2,2,3-trimethylbutane. Okay, so there's a lot. Those are the 9 isomers, and that's for a fairly small compound, heptane, C7H16. As these molecules get even a little bit bigger, then the number of isomers sort of skyrockets. I think there's 15 for octane, then it goes up to like 24 or 30 for nonane, and then like hundreds really rapidly. It gets boom, it just goes out of sight. So we need the ability to discuss structure, because these molecules here for heptane, these aren't particularly different. They're pretty close in size. They don't really have anything remarkable going on about their structures, so they have very similar physical and chemical properties. They are somewhat different. They're going to have slight differences, and that does matter. You try to do a reaction with 2,2,3-trimethylbutane, you're going to get very different results than if you try that same reaction with heptane. Okay, it's just you're going to get different things. Those differences in structures do make a difference. So we need the ability to talk about structures, and this is one way to do that. This is a better way. Okay? This right here is a 3D picture. It shows all the atoms, it shows all the bonds, it shows their orientation in space in 3 dimensions. It shows the different kinds of atoms we have here. So we have black atoms for carbon, white atoms for hydrogen. The red atoms are oxygen, yellow atom over here, that's sulfur. These blue atoms are nitrogen. So you can see the number of atoms there are, the way they form their connections, their orientation in space. We have these thick sticks for single bonds. We have doubled sticks for double bonds. So this right here contains a lot of information, and the program necessary to make this these days probably only costs $100 or $200. They might have them available at some of the computers there in the school. Or you might even be able to build something like this using just a program available on a web page. The way computers are advancing and developing now, this right here, this particular thing isn't excessively difficult. You could probably do that. But even this is a little bit too much, and it's way too much for them to expect you to be able to draw. You could not draw this by hand. This is what they would expect you to draw by hand, Lewis structures. Okay, you covered that in lab already. And this is easy enough to draw. This over here is the simplest and the wrongest. It doesn't have the lone pair up here on nitrogen, so that's just no good. This here is really good, and not only does it have the lone pair and the 3 hydrogen-nitrogen bonds, but it also shows some geometry. So this wedge shape right here, that's coming out of the screen towards you. This dashed line right here, that is going out of the screen back away from you. So it shows this sort of pyramid shape for ammonia. Okay, this line is in the plane of the screen. This is coming out towards you. That's going back away from you. Just a simple 3-pegged pyramid. This up here is a variant on organic chemistry. The way they do things there, called a Kekule structure. Each of these lines represents a bond, and where the line ends, it either bonds to a carbon implied. So here's a carbon at this bend, so this bond is between a carbon right here not shown and another carbon right here that's not shown. And then this line, it ends in an oxygen, so it ends explicitly in an oxygen. Then they also chose to end each of these bonds with explicitly noted carbons. There are also even more invisible hydrogens on this guy. Carbon likes to form 4 bonds. As you practice your Lewis structures more and more, you'll see that that's what carbon likes to do. So this carbon right here, it has its 4 bonds already full, carbon to carbon to carbon to carbon. But this carbon down here, it only has 2 bonds full, one up here to this carbon and one over here to this oxygen. So this carbon has to fill in those 2 remaining bonds with 2 hydrogens that just aren't shown. And there's a reason organic chemists do this. It's because if you do show all the atoms, it gets crowded really, really quickly. So let me go ahead and show you that. Let's see, there's 1 carbon, there's that, and there's that, 1, 2, 3, and then it bonds to an oxygen, which bonds to a hydrogen. This carbon has 2 hydrogens on it. This carbon is bound to 2 more carbons. Those carbons are each bound to 3 hydrogens. And this carbon is likewise bound to 3 hydrogens. So this is a fairly small and simple molecule. Oops, oxygen has lone pairs. So even so, you can see it gets really crowded really, really fast. And in fact, this way they've drawn it right here is not how they typically draw this in organic chemistry, because drawing the CH3 at the end of each of these chains just takes up a lot of time that they don't really feel compelled to do. So the way they actually do it is like that. And thus each line represents a carbon-carbon bond, or in this case the carbon-oxygen bond. Each line ends in a carbon, and you just have to remember that it's filled in with hydrogens. And if you practice organic chemistry long enough, this becomes more or less second nature. And the reason that, of course, they do that is because this, you saw me, it's just really easy to draw. And you can draw other things like the isomers of heptane. So here's heptane, 2, 3, 4, 5, 6, 7. There's heptane. Then here's the first isomer. Let's see, 6, boop. And then here's the other isomer, boop. I mean, it just gets really easy with a little bit of practice. And it lets them draw lots of molecules, big molecules, complicated molecules, really darn quickly. So that's why they do that. Now, you don't have to worry about drawing these here. And this is more on the, this is the high end of the scale of what I think that I don't think they might actually ask you to draw something like this. This is within the realm of possibility. It doesn't stretch you too far to expect you to be able to do this kind of multi-center Lewis structure. It's a lot, but it's not excessive. They absolutely, definitely, no doubt about it, will expect you to be able to do ammonia, and somewhere between these two. This, I think, is the far end of the spectrum of what they would expect. This is the low end of the spectrum of what they would expect. Okay. Ammonia is kind of the simple end, and this right here, let's see, that's 2,2-dimethyl propane. You don't want to talk about propane? Propane accessories? So that's kind of the high end of what they could expect. In the end, though, you absolutely have to get good at Lewis structures. So much depends on those Lewis structures. You have to be able to draw the Lewis structures, because that's the only way you can get molecular geometry and hybridization and polarity, and all those things are so important to chemical properties, chemical behaviors, reactivity. If you need to be able to do Lewis structures in order to succeed for the rest of the semester. Not just this next test, but the rest of the semester. It's absolutely vital. So practice. I understand this last lab was hard, but definitely practice. Remember, this is chemistry. It's hard for everyone. So there are like 5 million web pages dedicated to giving you practice problems and helping you walk through those. I'm also going to make up a quick lecture series, a set of videos for that. I'm actually going to do those tonight. to supplement on how to draw Lewis structures and how to do formal charges, because it's just that important. And remember, there's always Khan Academy. It's a popular series of YouTube videos. That Khan is spelled Khan, and Khan Academy. That's YouTube. He lectures on all sorts of stuff, and it is another very valuable resource. And of course, there's also the supplemental instruction. So that is it for the first bit of Chapter 4 here, and that is all you're going to need for Chapter 4 this week. I will see you, all of you, in class next week. Yay! All right. And with that, I'm done with this, and I'll see you again in maybe 5 or 10 minutes for a lecture on Lewis structures.